Well, I realize I'm the last thing that's keeping you from your dinner, so I'll try to be reasonably quick. And I promise I won't point at the screen with my foot. So this, I know. But I did wear my ski outfit for a tradition. The foot, oh God, it was got to be the mid-'80s. That was a Chris Russell plying me with wine problem. Anyway, what I want to talk to you about is data going back to the good old days. This is probably the piece of data that I waited the longest to work on. I discovered it back in 2001 and said, this would be cool to work on, and I set it aside, and I finally got a student who would be interested in working on it. So for the last couple years, we've been looking at a particular case where we had wonderful conjunction of auroral imaging, both from the northern hemisphere with image and the southern hemisphere with polar. Nikolai Osgaard has done a lot of work with that data set, looking mostly at the midnight. But what we wanted to do was to look at a different question, which was the east-west skew of the convection pattern. And I appreciate Helis, introducing the topic so I can go through this quickly. But if you've got a northward IMF case where very little BY, you can get a 4-cell convection pattern with the flow sunward in the middle polar cap and around on either side with a viscous cell, which is grossly overstated in size. If you've got a really strong BY, you can end up with a 3-cell pattern with the entire polar cap just going around in a circle. But if you start to have some negative BY or near zero, you can actually get a hybrid of these where you get a large orange cell and a banana cell, again in Rod's parlance, plus perhaps a lobe cell circulating entirely within the polar cap. And that lobe cell could be completely on open field lines, or it could actually open and close during its circulation cell. So that adds a certain amount of problems to that issue, okay? Well, if you look at northern IMF reconnection, and this is a really nice animation from Paul Kasek, you get reconnection at both polar caps very strongly northward, and then as the IMF turns to have a strong BY component, you'll notice the field lines can develop a very strong twist as they peel off, and then we're going to look in the back of the tail where they reconnect, and they actually reconnect coming in from the sides to reconnect. So a lot of the things that we think of are happening in the magnetotail are really torqued strongly when you have a strong BY component. So this particular event is one, guess what, we had a ginormous BY component starting off at about 31 nanoteslas at the beginning and decreasing to only 24 nanoteslas at the end. BZ started out near zero at the beginning, slightly negative, and ended up at minus 20 nanotesla at the end. As you can imagine, this was a KP 6 and 7 event when it happened. And this was the one that we then had auroral imaging over that entire time frame. And they're slightly different instruments looking at slightly different wavelengths, and so we chose an operational definition of the open-closed boundary as being about 2 kilorayleigh for Wick and about 6 kilorayleigh for Viz, because you can get a nice clean boundary of the polar cap from the aurora that way. And one thing you immediately notice is how shifted this is. This is about 5 degrees shifted toward dawn, and this is about 5 to 10 degrees shifted toward dusk in the southern hemisphere. Again, no big surprise for those of us who've looked at convection patterns all our lives. And here's the movie of how that 2 hours went. Kind of, you can see how well we can really identify the polar cap boundary. There's some hash here in the Morningside. Part of that is an aspect ratio, but also, as I'll show you, some of that we believe is the presence of a lobe cell. But as you can see, we had some pretty strong activity, some of it very conjugate, some not. I love this X Aurora at midnight on both. So what we then did was looking at the convection data, again, no big surprise, gigantic BY gives a very strong flow across the polar cap toward the dawn in the northern hemisphere, not as much in the southern hemisphere. Plus, in addition, now again you can easily see the dawn dust shifts where this boundary is right at 70, and it's hard to tell here, but it ranges, from 68 all the way up to 75 if you just looked at the particle data. Now those of us who've seen a lot of this, we recognize this as being the signature of the viscous cell. It's very narrow actually and easy to miss and sometimes doesn't exist. So one could argue that this is really the open-closed boundary, and this is the presence of a lobe cell. And we saw that then in this part of the precipitation associated with the lobe cell in the northern hemisphere, but not so much in the southern hemisphere. Again, that's not too surprising because lobe cells are more of a summer effect. But this is just sort of laying down what a 3-cell might look like on that data. We ran, just to see what a typical person would do with the data, we ran all 4 models at the CCMC. First we ran them like an idiot, like ourselves, and then we went back and asked Masha to help us tweak it up and got a little better results. So we ran all 4 models for the whole event and used it to predict what those models said would be the dawn dust shift of the open-closed feline. So we went and found the open-closed boundary in each of those models. And what we find is the bats or us all have this nicely symmetric open-closed boundary, nice and smooth. It does show a little bit of non-dust shift, but not a lot. If you then go to bats or us and LFM on this side and open GGCM, you see the open-closed boundary really gets crazy because this really strong driving is tough for these models to handle. We get an open-closed boundary that actually does show the shift. So they show more shift than the bats or us with or without the RCM, but much more ragged polar cap boundary. So we looked at the polar cap boundary operationally with the data and also then with those models, and just had a single measure called delta L, which was right at 618 line, and then subtracted them and got the dawn dust shift, where positive is shifted toward dusk, and then just got the polar cap width as the colatitude added up as opposed to subtracted. So first problem is, of course, trying to find the right operational level for our open-closed boundary operationally, and we're pretty comfortable with that number. The problem with finding the open-closed boundary in some of these models is that they had more than one. So here, for example, at 1800, there's 1, 2, 3 open-closed boundaries, and it's not too surprising because here is a very large lobe cell, clearly inside the first open-closed boundary, and a rotating convection cell on this side in the north, and on that side, again, completely inside the open feline region. So the presence of this lobe cell is what is causing this tremendous distortion of the open-closed boundary on this side in this model, and probably also in these as well. But so we had to get several possibilities as to the boundaries, and we kept track of the northern one most and the southern one most separately. So here's so here's the movie of the open-closed boundary from bats versus the data, and we see it's a little too circular and it doesn't have as much skew as the data. And then I will go on to the LFM equivalent. And again, their open-closed boundary is way far north. They've got a tremendous amount of reconnection in the tail. They've got their X line really close to the Earth because of this strong BY and BZ. But as you can see, the skew is similar, but of course the total area is about a factor of 2 too small, which means that reconnection is happening too strongly in their model. Okay, so we looked at these offsets versus BY. We looked at the offsets now using the high, the middle, and the low if we had multiple open-closed boundaries. And what we find is that, in fact, if you just now take a single number, which is the average over this whole 2 hours, the average dawn-dusk shift from the data is minus 8 degrees in the northern hemisphere and plus 10 in the southern hemisphere, and you compare with the bats. We're way larger than the bats as far as the total shift, but we're much more comparable in the shift with either the Open GCM or the LFM. And just another note, there is lobe cells visible in all of the models for this case. And this is just kind of a spaghetti model of one of them, just showing how crazy some of this reconnection tangles up with field lines that have those same kinds of twists. Okay, and so the summary then is that none of them did really well. Bats were too symmetric, Open GCM was and LFM were very irregular, and the LFM did the best. So we want to continue to work on it again, and of course we want to thank everybody who helped us provide data, especially Masha with helping running the models. Before I quit, I did want to say a couple of quick things. If you're not on my SPAC alert email list, we heard about the March event. This was our little Boyle index, which is an unsaturated polar cap potential drop. When it goes over 200, we send out a red alert. We did send out a red alert, so everybody who got them 3 hours ahead noticed that aurora was coming. And here's how we predicted 3 hours ahead KP versus how it came out. So for a completely empirical model, I think we're doing amazingly well. So if you're in a place where it has auroras and you want to get an email from us as to when there's aurora, let me know and I'll put you on the list. Finally, as a present for staying till the bitter end, I've got some of our outreach CDs over here so you can have one. Thanks.
When there's an IMF BY and a global MHD simulation, it can be very challenging to find the open-closed boundary, the separator line out in the magnetosphere. But possible. I mean, it can be done, but it's a lot of work. I'm just wondering how you did it.
We just trace the field lines. It actually, the automated functions that are on the GGCM worked like a charm. And we did the individual model, the mappings to make sure they made sense to what they were giving us.
I'm curious, for the Barcelona runs you've done on CCMC, do you know what kind of a conductance model being used?
What kind of reference model?
No, conductance, ionospheric conductance model.
Oh, just the standard one. We didn't put in any special conductance models.
Okay.
Again, we were just trying to see what it could do hands off. I'm sure you could actually go through and try to tweak it and enhance the conductivity or whatnot, but we just wanted to see what it would do with, like a regular person would run it.